Today, GPUs are more expensive than ever. Nobody can get as many as they need, and it's so extremely important to keep utilization high and avoid wasting cycles. With that in mind, I'm gonna go ahead and crash this model training job. It's been running for an hour on my GPU, and I'm just gonna kill it. Oops, that is time and money lost forever. Thankfully, this is just running on my laptop. But when a GPU goes down for real, if you're lucky, brittle auto-resumption and job recovery systems might kick in for key production training jobs, but probably not for your experiments. It's on you, maybe your ML engineers, to dig around for the latest checkpoint, build a new configuration, or in some other way attempt to resume where you left off. But it doesn't have to be so difficult. I'm Sam Ingbar. I'm a solutions architect at Temporal, and I also spent years helping build production ML pipelines for everything from simple LSTM models to frontier LLMs. And if you connected with that anecdote even just a little bit, you're like me. I want to tell you today about how we can do things differently to improve your GPU utilization, build complex pipelines that are stable and reliable, and avoid some of the pitfalls that come with graph-based systems all at the same time. For example, let me show you what Temporal is capable of by coming back to our worker. I have not written any orchestration code that will relaunch or restart my job. I'm using PyTorch to do some checkpointing, but Temporal is what's going to provide free orchestration and resumption. So let's start the worker again. Here we can see it resuming from 25%, or the latest checkpoint for this training run. Again, I didn't write a single line of code to make this happen. This is just a small piece of the value that Temporal will offer you in MLOps. So over the next few minutes, I want to lead you through a quick overview of Temporal and run an experiment to show you what Temporal is capable of. So in order to do this, I needed to build a use case. And I settled on a hyperparameter optimization use case for a small language model that would use a scaling ladder approach to demonstrate how you can save time and money on your GPUs. So my approach is roughly based on a 2017 paper called Hyperband, a novel bandit-based approach to hyperparameter optimization by Lee and others, and some work I've done in the past. And so today we'll be using this workflow to show how we can optimize our hyperparameter tuning to save time and money on GPUs without relying on black box algorithms. And at the end, our goal here is going to be to make the model better at determining if a statement has positive or negative sentiment within a fixed compute budget. We'll be using the BERT model and training it on the GLUE SST2 dataset. Breaking that down just a little bit, first off, hyperparameters are settings that impact how the model looks at the training set and learns from it. So our goal in this experiment is going to be to run two different training runs. We're going to first take one that takes a total compute budget for the entire thing, takes half of it, and says, okay, we're gonna experiment with different hyperparameter settings for half of that budget using this scaling ladder approach, which I'll come to in a second, in order to get to the best possible configuration we can with making some reasonable assumptions. And the other one is just going to be a straight random hyperparameters, use 100% of the budget on training. And so what's going to happen is our run that uses our ladder is going to train on less data. But my hypothesis is that it's going to be cheaper to do, or the same price in terms of GPU hours, and it's going to be more accurate than just a brute force approach with random hyperparameters. And so with that in mind, it's good to know a little bit about hyperparameters. So hyperparameters, as I mentioned, they're settings that impact how the model looks at the training set. And if you're not aware, hyperparameters matter as you start to scale up your training. When you have a small model, the data you show it is going to have a far bigger impact than the hyperparameters will in terms of how accurate that model is at performing a certain task. But as we start to use more and more and more data, the hyperparameters, which shape how the model learns from the data, can actually have a bigger impact on the final accuracy of the model than the quality or quantity of the data we train it with within certain reasonable bounds. So how do we actually pick our hyperparameter values? Well, there's a few approaches, and I'll talk to you about them and then which one I'm going to use. So the first is this total random selection approach, which is exactly what it sounds like. That is what our sort of control run is going to use. We're just going to pick random hyperparameters totally at random from this massive range of possible values and see how it goes. Another option is called grid search. Grid search is where we take a range, the range of possible values, and we exhaustively search it, with every possible value. Our goal is to get 80% of the result of grid search, but with 5% of the effort. And so one way to do that is a method called progressive optimization. That's what we're going to do. I'll talk about that in a second. But a fourth option, just to put it out there, is you use a third-party algorithm when you make it somebody else's problem, basically. We're not going to do that. There are drawbacks to that, like you don't know how the algorithm works. If you want to publish on your research, it can be tricky because you're like, I use this algorithm and I don't really understand how it works under the hood. It's also difficult to modify because of the same reasons, and so there are times where they're great and times where you want to do your own thing. So we picked progressive optimization, and that means what we're going to do is we're going to learn as we go. And I like to think of this like a game of Battleship. I start with total random selection. I pick a grid square that is essentially random. I may have my like personal strategy, but it's mathematically pretty random. And then when I get a hit, I start to hone in on an area and saturate it because I know that area is more likely to have a ship than some random square that I pick out of the blue. So here we're doing the same thing, basically. We're starting with like 100 configurations that all have random values. We're gonna train them just a tiny bit on a small amount of data and look at the performance. And we're gonna pick the top 3 and we're gonna keep those. We're gonna throw away the other 97. And then we're gonna generate 47 new configurations that are based on those 3 winners, but slightly different. And we'll basically repeat this, cutting down and generating new configs until we're down to 1 config left or we run out of our budget allocated. And then we'll take the best one and we're gonna use that to do the rest of the training. This looping process is called the scaling ladder, which is a term I've used throughout the video so far. Why are they important? They've been shown to reduce GPU costs for real training runs by 70 to 95% compared to grid search, while getting similar quality results in terms of their parameter settings. And obviously, like, it varies a little bit depending on the exact method and study, but they're super effective for this process. And so you might be wondering, like, does our sample code actually do all this stuff? And what does it have to do with temporal? So let's now kind of connect the dots here. The training job we saw at the beginning is actually part of this experiment that I'm describing. It's running as we speak. And so let's look at how we can use temporal to build that experiment and what that looks like. If we think about building a scaling ladder like I described, we might approach this in a normal sense with like a notebook, and we might start by writing functions that say, hey, here's a function for generating some configurations. Here's a function for training. Here's a function for evaluation, winner selection, running the comparison and calculating some metrics. And then, maybe we'll create a loop that uses those functions to essentially run the ladder logic. And then we'll hit go and it'll print out like a nice little model card comparison of our models and how much we improve the accuracy, and we're done, right? Well, not so fast. The notebook-oriented solution is a little bit dead on arrival the moment everything moves off of your laptop. How would we recover if there's a crash? Do we just restart from scratch? We need a system to handle that. And how do we keep track of the overall state of the ladder to facilitate that recovery? We also need to have some kind of state management for that. And we need to monitor progress of the job. That's another system potentially that we need to set up and maintain. And so all these systems can also fail, and the complexity here starts to build. By the time we're done, we'll have written hundreds of lines of retry logic and state management, failure handling, even if we're using well-established orchestration solutions like step functions, prefect, airflow, and so on. And so if we think about this a little differently, I think it's fair to say that many of the ML systems problems are distributed systems problems. And so with that in mind, temporal is a great fit for solving these problems because it's exactly what it's meant to address. With temporal, the way that we do things is we have a starter app, like a notebook, and we use it to send a message to temporal service. And temporal service will coordinate doing work with temporal workers. These workers are actually pulling temporal service for work, as you can see in the diagram. They then execute it and they let temporal know, hey, here's the outcome of this work. And temporal service is going to persist it durably in this event history. And this approach is really great because it allows us as developers to focus more on writing core business logic. And we let temporal service sort of orchestrate the retries and handle state management instead of us. So in my case, I use temporal to create 4 workflows, and they all work together to create the ladder. So first I created a training workflow and an eval workflow, and then I reused those in this coordinator workflow where it launches those as child workflows to run an individual rung in our ladder. And then I built a ladder workflow on top of all of this that handles like building the trials, creating the new configs, launching the coordinator, doing ranking and promotion at the end once the coordinator returns all of the trial results, and finally selecting a winner. And so that's like the top level workflow. And what was great about this is everything was, completely code native and reusable. So once I wrote the training and eval workflows, which took longer than the coordinator or the ladder workflow, it was very easy to then reuse them in my higher level workflows and start building out these pipelines in a matter of hours. So let's make that concrete. Here we can see the workflow definition for the training workflow in that diagram that we were just looking at. And you can see that it's written as a Python class. We have our CheckpointedBertTrainingWorkflow here, decorated with this workflow definition decorator. Within it, I have some state variables that I set up when we initialize the class. I have a function decorated with workflow.signal, which lets me send information to this workflow while it's running. I also have a function decorated with workflow query. This lets me query the state of the workflow and see what's happening programmatically while it's running or after it's completed. And then I have my main workflow description in this run function decorated with workflow run. And so here we can see that it consumes the config, it snapshots the data set, it then runs checkpoint aware fine tuning. And basically the way that we're doing that is quite simple. We're building a request, and then we are basically saying, hey, workflow execute activity, the activity name, our request specifications that basically gives it input parameters, and we're setting a start to close timeout of 2 hours in this case. So this is what our workflow code looks like. It's super simple, but it's quite descriptive, and it allows you to tune like retry behavior, timeouts, things like that. Flipping over to activities, here we see the BERT fine-tune activity class, which defines our fine-tune BERT activity we were calling in the workflow we were just looking at. And you can see it has a similar structure. We have a Python class, we have some state variables that are specific to our activity. We then have a number of helper functions that we use inside of our activity definition. And then we have our main function here, decorated with activity definition, called fine-tune BERT. And this is where we actually do our PyTorch training. And this actually looks a lot like you might see like a notebook or a script or any sort of common training code that you sort of run into in the wild, which is really nice because it makes it easy to adapt those existing scripts or notebooks into Temporal and give it the durability that Temporal provides. Here we can see the Temporal UI, and this comes out of the box with Temporal standard, no special integration needed for this. But it lets you see the progression of your workflows in real time. And so we can see, for example, this create dataset snapshot activity happens here. We can see this fine-tuning activity is scheduled here at 5 minutes and 14 seconds. We can see that it's picked up somewhere around 8 or 9 minutes in and then completed successfully here at the end. We can also see these signals being sent to our sort of parent workflow, letting it know about these updated checkpoint directories so that it can pull from the latest checkpoint. And we also can see inputs and outputs for each step. So here we get a config as an input, we get a result. If there's a failure, we'll be able to see the retries and we'll be able to see what the cause of failure for each retry was. So it's sort of a one-stop shop for monitoring your jobs. It doesn't replace something like TensorBoard, which can also be integrated with your temporal training runs, but it gives you, from an orchestration point of view, a clear lens as to what's going on with your job in real time. So good news, our experiment is actually finished in the meantime. And so let's take a look at the results. If we zoom in down here on our findings, what we found, we did a small experiment. We started with just 12 initial experimental jobs in our first rung. So pretty small scale, but what we found is that our experiment was about 10.1% more accurate than the baseline, which was the random selection model trained on twice as much data. And so basically by fine-tuning our hyperparameters, we used half the data, we got 10% better performance of our model, which is awesome. And that number should continue to increase with scale. So as we use more and more data or do more and more trials, we should get a better and better parameter tuning. And because we're using more data, it should have a bigger impact on model accuracy. So this is an awesome indicator that we're in the right direction. And I have scaled this up, usually gets to around 95% accuracy at larger scales and tends to plateau somewhere around there. So we could see even more improvement with a bigger scale experiment. So coming back to sort of recap what we've seen. First, Temporal will help give your ML workloads durability for free. You can write just business logic and then send durable messages for querying or signaling your workflows without worrying about recovery code or complex edge case handling. In addition, your runs will be easy to reproduce. You'll be able to create these complex pipelines with just code and then reuse them really easily. And third, you won't need to jump through any major hoops to adapt your code to work with Temporal. You will need to do some adapting, but you're not moving too far off of the format you're already familiar with, so you can take that notebook you've been working on for a month and in less than a day have it running on Temporal. Finally, you can still plug in other Python libraries that you want to use while you're using Temporal, and it should not directly impact your ability to also use Temporal. So one thing you may be wondering is, what are the trade-offs? And so I want to just lay them out. First, as I mentioned before, you will need to do some refactoring of your code. This involves separating deterministic workflow code from activity code, which should be idempotent. And especially your first time around, this will require a little bit of learning and thinking, so just plan for that. You'll also potentially have a tiny bit of additional latency from the network calls that Temporal is making between Temporal workers and Temporal service. This really doesn't impact you much, except the one sort of caveat to be aware of is probably don't try to do like low-level training coordination of one run across multiple nodes with just Temporal. Use like a specialist library like Ray or something like that to handle that piece, and then have Temporal kind of wrap that and provide durability. You'll just have more success with that approach. But those are the big drawbacks. So if you want to take action and do this yourself, I have a couple recommendations for you. The first is take a look at the Temporal AI Cookbook. It's on GitHub. It has the code under the MLOps folder for this demo. That will be a great place to see how I've done what I've shown you here, and it should inspire you with your own ideas. As you get started with Temporal, take the Temporal 101 course. It is thorough. It gets into the foundations that every Temporal builder, AI or non-AI, needs to know, and it will set you up to be really successful, not just at building your first workflow, but even teaching your peers and doing a lot of work with Temporal. And then third, I'm working on an Instruct course that will sort of walk you through step-by-step building this scaling ladder example if you want something, you know, even more hands-on and sort of step-by-step. I'm hoping to have that done in February. We'll see exactly when the final product gets out there to the world. Feel free to ask your questions to me in the meantime. Thank you guys so much for watching, and I look forward to your questions. Have a great day.